Okay, so welcome to week 12's problem solving session. Today we'll solve some problems related to week 12's assignment and then we'll also look at the week 11's assignment. So let's start. Let's start by recalling what we did in the class this week. So this week we completed the proof of the Valent-Fazirani theorem. So recall that last time we had started the proof of the Valent-Fazirani theorem, which basically says that if you have any S, which is a subset of 0, comma 1 to the n, and pick uh, vectors W1 to Wn uniformly at random from 0, comma 1 to the n, and define the set S0 to be S, and the set Si to be the set of all vectors in S which are orthogonal to V1 to Pi, then with probability at least 1 over 4, the size of one of the SIs would be 1, right? So last time we had started the proof of this theorem. Today, this week we completed it. And after that, we looked at the natural proofs barrier by Rasbarov and Rudich. And so to understand this better, we first need to understand what a natural property is. So a natural property is defined as follows. So let Fn be the set of all Boolean functions on 0, comma 1 to the n. So they are all n-varied Boolean functions. A property, Cn subset of, okay, so a property is going to be a family of subsets of functions. Okay, so this is a family because it's parameterized by n, and for every n, you have a subset of fn. So this is a family of subset of functions. So a property Cn subset of fn and in n is said to be a natural property if there exists a Cn star. Uh, if for all n there exists a Cn star subset of Cn such that Cn star satisfies two properties, constructivity and largeness. So constructivity says that whether a function fn is in Cn star or not should be decidable in time polynomial, but in the size of the truth table of the function. So I want to decide something about the function, and I want to say that this thing can be decided in polynomial time, right? But when I say that it is decidable in polynomial time, what I mean is that it is decidable in time polynomial in the input size, right? So over here, the input is the function, and a natural way to give a function as the input is to give its entire truth table. So the running time allowed is polynomial in the size of the truth table of fn, that is poly in 2 to the n. Because an n-varied function, the size of the truth table of an n-varied function is 2 to the n. Basically, you just need to specify what the value of the function is at every point in the Boolean hypercube. That string is how we represent it. And the second condition is largeness. And it says that the size of Cn star should be at least 2 to the order minus n times size of Fn. So, okay, over here, 2 to the order n is, okay, this is 1 over poly in the size of the input, right? So this, what this is saying is that with inverse polynomial probability, your function should lie in C star n. Okay, okay, so a property Cn, n subset of n in n is said to be useful against a circuit class script C if for all n greater than equals to 0, then Fn in C, Fn in Cn, Fn is not in C. Okay, so what this basically says is that for every function having this property, the function cannot lie in the circuit class. And this would help us prove lower bounds because, okay, so if a property is useful for against a circuit class, then using that property you can hope to prove lower bounds because it all you have to do is to show that okay, all you have to do is to show that okay, so no function having this property can lie in script C. So all you have to do is to show that there exists an explicit function having this property, and then you're done. Right. Okay. So That's why it's called useful against a circuit class. And a circuit lower bound against a circuit class script C is said to be a natural proof if a natural property useful against C is used in that proof. In other words, if a property that is constructive, that satisfies constructivity, largeness, and is useful against C is used in somewhere in the proof. Or you can like extract out of the property from the proof, then the proof is said to be a natural proof. And what Rasborough and Rudich show is that there does not exist a natural proof for NP not containing P slash poly unless pseudo-random generators do not exist. So here I'm stating the theorem slightly informally. In class, we saw exactly what parameters of the pseudo-random generators uh, were involved in this theorem, right? And we also saw that some of the proofs that we have seen in the previous lectures, like Hasta's proof, uh, are actually natural lower bounds. So using those so what this theorem says is that using those techniques, you cannot hope to separate NP from P slash pool. Okay. So yeah, that's what we saw in class this week. So now let's move on to problems. Just give me a minute. Okay, yeah. So now let's look at the problems. So the first problem that we look at is the following. So recall that in the proof of the Parent-Vazirani theorem, yeah, we used this fact. Uh, yeah, so we use this in the proof of Valent-Vazirani theorem. So now let's prove this. Okay, so the proof is by induction. Okay, so now what should the base case of this induction be? Now, normally the base case of the induction is usually 0 or 1, but in this case, the smallest possible value of m is 2, right? Because if m is less than 2, then this is 0 and this doesn't even make sense, right? So the base case is 2 in this case. So base case So what is 1 minus sum over I 2 to m 1 over 2 to the I? In this case, it's just 1 minus 1 over 2 square, which is 1 minus 1 over 4, which is 3 over 4. Also, product I 2 to m. Again, this is 1 minus just 1 minus 1 over 2 square, which is 1 minus 1 over 4, which is 3 over 4. So the claim is true. And so now let's look at the induction step. So first we need to see the induction hypothesis. And the induction hypothesis is that assume so let's start with the right hand side from this product. So I can write this product as this. Right. So I'm just writing the final term over here separately. So now by the induction hypothesis, this is greater than or equals to 1 minus, so product I to m. This is equal, okay, this is at least 1 minus some I to. So when we multiply, we get 1 minus 1 over 2 to the m minus. This is 1 minus some I in 2 to m 1 over 2 to the I plus. Now this is a positive number, right? So this thing is greater than or equals to 1 minus some over. I lost connection. Okay, never mind. And this is exactly what we wanted to prove, right? Yeah. Yeah, done. So now let's look at the next problem. One, two, so next problem. Uh, so what is yes? So this the probability looks very much like the probability in that we bounded in balanced by Rana-Fuzzy-Rani theorem. The only difference is that over there, the number of vectors that we picked was the same as m. Oh, oh sorry, it was okay. So let me write m minus. Yeah, so over there we picked m minus one vectors, and over here we are picking I vectors, where I is some number less than equals to m minus one, right? So you can think of this as a generalization of what we proved over there. Over there we proved it for one specific value of I, m minus one. Here we want a bound for a general value of I, right? Okay, so the proof is mostly similar, but let's see. Okay, so if W1 to are linearly independent, then W1 can't be zero, right? So 2 to the m minus 1 possibilities, and this implies 2 to the m minus 1 possibilities for W. Wireless connection again. Yeah. Similarly, if they are linearly independent, then W2 is not in the span where 2. So yeah, this is not in the span of W1, right? Now, what's the span of W1? Span of W1 is any vector which is a linear combination of W1, right? And since we are working over F2, there are only two constants, 0 and 1. So span of W1 is 0 times W1 and W1. So there are two vectors in it, right? So you have 2 to the m minus 2 possibilities. Similarly, if they are linearly independent, then W3 is not in span of W1, W2. Okay, so W3 is not in the span of W1, W2, which means that W3 is not a linear combination of W1 and W2, right? So W3 does not look like lambda 1 W1 plus lambda 2 W2. Okay, so how many vectors do look like lambda 1 W1 plus lambda 2 W2? Since we are working over F2, there are two possibilities for lambda 1, two possibilities for lambda 2, so there are four possibilities, right? So there are exactly four vectors in the span of W1, W2, and so there are 2 to the m minus 4 possibilities for W3. Similarly, Wi is not in the span of W1 to Wi minus. Yeah, so if it's not in the span of if okay, so one way to find this number is to look at how many vectors are there in the span of W1 to Wi minus 1. Again, a vector in the span looks like lambda 1 W1 up to plus up to lambda I minus 1 Wi minus 1, right? How many possibilities are there for lambda 1? 2. For lambda 2, 2. And so on for lambda I minus 1, also 2, right? So the number of vectors in the span is 2 to the I minus 1. And so the number of vectors not in the span is, okay, so therefore, I can just copy. This is uh, equals to product I. Okay, so what's the form? Okay, yeah, let me product I in 0 to I minus 1 to the m minus to the I minus 1. Oh, I can't use twice. That means J. And this is equal to, so I can take 2 to the m outside and cancel it out. So it's 1 minus 2 to the j minus 1 minus m. Mhm. So it's m minus j plus 1 minus j plus 1. So I need to start from that's product j 1 minus 1 over 2 to the m minus uh, oh wait, wait. So 2 to the 0 to, oh wait, this is j, yeah. Because I'm going from 0 to I minus 1, not to 1. Yeah, so this is 2 to the j. So again, you have 2 to the j. You have j over here. Yeah, so it's this. Yeah, so the property is this. Okay, so now let's look at third problem. It's similar, but over different field. So what is here P is some prime number. So this is just the property over here is just like that in the Valiant-Masrani theorem, but over here the field is Fp to the n. So Walid-Vazirani theorem, the probability in the Walid-Vazirani theorem was a special case of this, where their P was 2. Now P can be arbitrary, right? So again, the argument is similar. So and this implies k to the m minus 1. So W1 is a vector in Fp to the n. So for every coordinate, you have P possibilities, there are m coordinates. So P to the m and minus 1 for 0, right? Similarly, if W1 to Wn minus 1 are linearly independent, W2 is not in this span of W1. And this implies, yeah, so the span of W1 is 0 and 1. So you need 0 and W1. So you need to remove two vectors. Uh, oh, wait, no. Yeah. You need to remove k vectors because p vectors, yeah. Because now the span of W1 is alpha times W1 for any alpha in Fp, right? So alpha can take values from 0 to p minus 1. So there are p such things. Span of W1, W2. Okay, so what does any vector in span of W1, W2 look like? Again, lambda1 W1 plus lambda2 W2. And lambda1 and lambda2 are both in Fp, right? So there are p possibilities for lambda1, p for lambda2, and so p square possibilities. And so there are p square vectors in this span. So the number of vectors not in this span is, and in general, and this implies that, okay, so any vector in the span of W1 to Wi minus 1 looks like lambda1 W1 plus lambda2 W2 plus all the way up to lambda I minus 1 Wi minus 1, right? Now, lambda1 to lambda I minus 1 are going to be in Fp, and so lambda1 has p possibilities, lambda2 has p possibilities, and similarly all the way up to lambda I minus 1, which also has p possibilities, right? So there are p to the I minus 1 vectors in this span, and so we need to remove p to the I minus 1. Yes, so this probability, I will just copy. No, p to the I because I go from 0 to, uh, yeah, Okay, so this is 0. I'm going to what? Okay, so W1 corresponds to 0. Wi minus 1 corresponds. So Wi minus 1 corresponds to n minus 2. Wait. Okay, so W. Oh, yeah, so this should be n minus 2. Wait, I did a make a similar mistake in the first one. W1 corresponds to 0. I. Oh, okay, I and I minus 1. So yeah, this is fine. Here it's n minus, and yeah, the minus. Okay, yeah, so here it was I and I minus 1 and a minus 1. This is p to the I because, okay, let's recheck. So the first term is for W1. W1 has ONS connection. Um, W1 is p to the m minus p to the 0. So p to the m minus p to the 0, fine. And Wn minus 1 is p to the m minus p to the m minus 2. Okay, so Wm minus 1 is p to the m minus p to the m minus 1 minus 1. So p to the m minus 2. And yeah, so it's the m minus 2. So it should be I. And this is, yeah, so I can rewrite this as, yeah, yeah. And again, so this is the exact answer, but just like we proved, yeah. So now let's, okay, so what we'll do is we'll get this exact value and then try to compare it with what we get in the Waldenstone theorem, right? So, so I want to lower bound this, so I want to upper bound this, right? So this is less than or equals to, say, like 2 to infinity, 1 over p to the I. So this is 1 over p square, and this is, this is a GP whose starting term is 1 and whose common ratio is 1 over p to the I plus 1 over 1 over p to the I. So it's 1 over p. So 1 minus 1 over p. And this is 1 over p square times. Yes, so it's this. And if you put 2 over here, you get 1 over 4. Yeah. Yeah, so is this fine? That's the next problem. Okay, so the next problem is the following. If it is a multilinear polynomial where f2 of degree, let's say, less than equals to two. So the question is Cn constructive? Yeah. So, okay, so first of all, recall that we know that every function has a multilinear polynomial over f2. However, the degree can be as large as n, right? And in this question, the degree is at most p for some number d, which you can think of d as constant or log n or root n. It is going to be less than n. It's going to be smaller or smaller of n. Okay. So let's see if this is constructible or okay. So okay, uh, fn in Cn if and only if there exists uh, alpha e such that fn okay, so that such that for all b in let me write it like this, so that multilinear, the unique multilinear polynomial then right, some word e uh, alpha e and for all e such that okay, so over here e is going to be a subs yeah, so e is a vector in 0, 1 to n, and every vector in 0, 1 to n corresponds uniquely to a multilinear monomial. Yeah, so that's why I'm indexing with e, and alpha e is the coefficient of this monomial, and this monomial is x1 to the e1, x2 to the e2, up to xn to the en. Okay, this is just a shorthand for this monomial. So fn is in Cn if and only thi- if this is the polynomial for fn, then for every e such that its Hamming weight is greater than b, alpha should be 0. Okay, so the Hamming weight of a monomial is equal to the degree of the monomial, right? Because every so this is a string is 0, 1 to the end, and the degree is going to be exactly the number of indices that are 1, right? That's exactly the Hamming weight. So Fn is in Cn if and only if this is true, right? Now will show how to decide whether fn is in Cn or not using a linear uh, by solving a linear system of linear equations. And for those of you who are familiar with interpolation, this is almost a lot. This is a lot like interpolation. Okay, so consider uh, m y equals b. Okay, I think we can skip the vectors. Yeah, rather than where okay, let me go step by step. Okay, so where y is in f to the m, f2 to the m plus um, capital M is matrix. Let me say it's f to the n plus k, where k is oh, I lost connection again. Just the k is yeah, so k is this. Okay, what is k? So this n choose I is equal to the number of monomials of degree, number of multilinear monomials of degree exactly I, right? So this is the number of multilinear monomials of degree uh, exactly, uh, okay, sorry, degree at most d, right? So this is the number of monomials with degree at least d plus 1, right? So y is going to be, okay, y is n plus k dimensional, a vector of variables. K is this. Yeah, so it's a vector of unknowns. And what we will end up doing is that we'll, y would essentially end up being the coefficients alpha e of the polynomial. Oh, wait, I made a mistake somewhere. But this should be, yeah, it's 2 to the n. Yeah, so, wait, no, wait, no, I made a mistake. This is going to be, okay, this is 2 to the n, yeah. Uh, yeah, this is going to be 2 to the n, so these are going to be the coefficients. K will come in later. So y is a two-dimensional vector of unknowns, and these are going to be the coefficients alpha e, right? So there are 2 to the n coefficients, 2 to the n unknowns, right? Now b is in F2, 2 to the n plus k, where k is this quantity. Yeah, okay. And M is a matrix in. Okay, so generally when you interpolate, you have 2 to the n unknowns and 2 to the n evaluations. Here we are slightly more equations, and that's to enforce these constraints that like we are zero. Okay, so now okay, so I've told you how m and y what are the the number of rows and columns. Now I need to tell you what the entries are, right? So B1, B1 comma B2, where B1 is in yeah, this is in K. Yeah. Uh, for all E, so by B1 E, I mean the eth entry of B1. So I can, since B1 is in F2 to the 2 to the n, I can index the entries of B1 by elements, by strings, right? Strings is 0, 1 to the n. B1 of E is Fn evaluated at E, and for all okay, all entries of P2 are 0. Divide similarly, divide M1 is in okay, so for all E in 2 to the n, M1, so M1E is a vector of size 2 to the n, right? And I'm saying that this vector is going to be E. Oh, wait, no, this shouldn't be E. Oh, yeah, this should be this vector. So basically, all the multiple monomials in E1 to n. Okay, and for all E in 2 to the n, such that this is greater than B. So what I'm doing is M2 has exactly k times k rows. So I can index every row of M2 by vectors E such which degree greater than B, right? and there'll be uh, uh, one in the th entry and zero everywhere else. Oh, I lost my connection again. Okay, so now that we consider this system of linear equations, let's prove that the solution of this system. Okay, so I think the reverse direction is easier to get first. Okay, so Fn is in Cn, which means Fn is a polynomial of this form, right? So my claim is okay. My claim is that okay. So let's see why. So let's try to understand what this system of equations is does. Okay. So now, for now, let's focus on M1 and B1. Okay. So and okay, let's look at the earth row of M1. So let's look at M1E. So when I multiply M1E with the vector Y, I am getting B1E, right? So uh, any system, so any vector Y which satisfies M1Y equals B would be a set of coefficients for a polynomial which evaluates to the same value as uh, Fn over the Boolean hypercube, right? Why? Because plug in the coefficients over there in place of um, y. So what do you get? So you get alpha 0 times 1, alpha e1 times e1, alpha e2 times e2, alpha e1 e2 times e1 e2 and so on, right? So this times alpha 1 to alpha, the vector of alphas is exactly the evaluation of the polynomial whose coefficient is alpha 1 to alpha n, right? Yeah, so I kind of have this a little, but yeah, you can fill the details on your own. So alpha is our solution of M, and so one direction is done, right? So now let's look at the other direction. So a solution exists. Let's say alpha, then So if a solution exists, then my claim is okay. Then from what I just said in the for the previous case, this we already have already seen, right? But we additionally need this to argue that F is in Cn. But this is easy because now let's look at M2y equals B. So what does M2y equals B2 tell us? So if M2 alpha E equals B2, then let's look at for a fix an E and let's look at M2E, right? So what is M2E? It has 1 in the Eth entry. So M2E is going to pick out alpha E. And what is B2E? B2E, all it is of B2 as well. So B2E is 0, right? So what the so the Eth constraint in M2y equals B2 tells us that the Eth alpha, the Eth entry of alpha, that is alpha E, has to be 0. So this is also satisfied. And this implies that, okay, so if we can decide whether this thing has a solution or not, then we can decide whether Fn is in Cn or not, right? So now we need to decide whether this is a solution or not. So using Gaussian elimination, we can decide uh, solution in time, Pauli in the dimensions of m, right? So Pauli in 2 to the m, comma k, but k is at most 2 to the n, right? So this is just Pauli in 2 to the n. Yeah, so in polynomial time, in the truth in time polynomial, the truth table of the size of the truth table of f, we can decide uh, whether fn is in Cn or not, and therefore it is constructible, right? So it's very constructive. Yeah. Now let's look at problems from 11th assignment. Hmm. Oh wait, I had one more problem for 12. Yeah, almost forgot. Yes, so the fifth problem is similar. So does the Cn satisfy? So we know that each function, so the size of Cn, okay, so how many such polynomials are there over F2, right? Oh, we can charge. Yeah. So let's see how many such polynomials are there over F2. So uh, okay, let me do some. So recall that till n over 2, the binomial coefficients increase. So this is represented by this, and this is equals to root. Okay, which is upper bounded by, and this is okay. Yeah. S- Therefore, so in any polynomial, you have these many monomials, at most these many monomials. Right. Oh yeah, I forgot. That's great. And over here, yeah. So this is or this is n to the order root. Yes, yeah. So you have these many monomials. Okay, I think I should simplify this further. Yes, the number of polynomials of degree at most p. So any polynomial of degree at most p has these many monomials. And for every monomial, you have two possibilities for coefficients 0 and 1. So the number of monomials, so the number of polynomials is 2 to the 2 to the, and okay, and what's the size of Fn? So the size of Fn is equal to 2 to the 2 to the n, right? And what do we want to know? We want to know if this can be obtained by just dividing this by 2 to the n, right? Now, size of n, and this is much larger than, so this is capital. Yeah, because uh, 2 to the n minus O1, so O1 is just a constant, right? Oh, wait, did I? Oh, this will be O n, yeah. So 2 to the n minus O n is much larger than this. Yes, so this is like at most n to the 0.51, and this is 2 to the n, right? Yes, even if we are subtracting a small quantity, this is still much larger, and so Cn is not constructible. It's very large. Cn does not satisfy largeness. Okay, so now let's look at problems from the 11th assignment. So the first one is out of the following, there are three models which are for which the respective classes of polynomial side circuits branching programs are the same. Pick the model which is different. Permutation branching programs over S3, mod 3, mod 2 circuits, AC03 circuits, and mod 3, mod 2 circuits. And the number of mod 2 gates that evaluate to 1 is 0 or 1 mod 3 for each pin. So we saw that these three are equivalent. So we know the answer is this, but why is AC03 different? So recall that we showed that parity is not in AC0. So parity is not in AC03. However, parity can be computed over here easily, right? There is no mod 3 gate, just a mod 2 gate. So parity is here, parity is here, parity is here. We know all these three are the same, but parity is not here. So AC03 is the odd one out. So now let's look at the next problem. So the next problem is which of the following sets of permutations generate S3? Options are 1, 2, 3, 1, 2, 3, 3, 2, 1, 1, 2, 3, 2, 3, 1, 1, 2, 3, 1, 3, 1. Let's look at all the options. So A is 1, 2, 3, right? So 1, 2, 3 to the 0 is 1, 2. So recall that to generate S3, uh, every element of S3 we should be able to write every element of S3 is just a combination of these, right? So for 1, 2, 3 to the, so if 1, 2, 3 generates S3, then I should be able to write every element of S3 as power of 1, 2, 3, right? So 1, 2, 3 to the 0 is 1, 2, 3. The identity permutation 1, 2, 3 to the 1 is self. 2. So 1 becomes 2, 2 becomes 3. So 1 becomes 2, 2 becomes 3, so it's 3. 2 becomes 3, 3 becomes 1, so it's 1. 3 becomes 1, 1 becomes 2, so it's 2. 3, 1, 2. 1 becomes 2, 2 becomes 3. Wait, what is made a mistake. Right. 1 becomes 2 and 2 becomes 3. Uh, 2 becomes 3, so 3. 2 becomes, oh, no, 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 yeah. I miswrote, yeah. So I, I should write what 3 becomes. Yeah, so 3 becomes 1 and 1 becomes 2, so 2 and 2 becomes 3, 3 becomes 1, so 1. Yeah, so it's 3, 2, 1. So 3, 2, 1, 1, 2, 3 is okay. So over here 1 becomes 2, over here 2 becomes 1, so this is 1. 2 becomes 3, 3 becomes 2, so it's 2, and 3 becomes 1, 1 becomes 3, so it's 3. Yeah, so uh, the group generated by 1 to 3 is just these three permutations, and so this does not generate the group S3, which has 6 elements. So this is false. Now, 1, 2, 3, comma, okay, the group generated by 1, 2, 3, because 3 to 1 is, yeah, so 1, 2, 3 generates 3 to 1. So the group generated by 1, 2, 3, comma 3 to 1 is just the same as group generated by 1, 2, 3. So this is also not generated. So what about 1, 2, 3, comma 2, 3, 1? So we saw last time that this does generate G3. So this is true. Okay, let me give you a reference. Yeah, problem 1. We can have, what about D? So first of all, notice that 1, 2, 3 compose with itself. So 1 becomes 1 and 1 remains 1. 2 becomes 3, 3 becomes 2, so 2 becomes 2 and 3 becomes 1, 3. Yeah, so yeah, so uh, yeah, so 1, 2, 3 does not generate the first permutation does not generate S3 because this to the 0 is 1, 2, 3. This to the 1 is itself, and this to the 2 is again identity, right? Now these two are the same. Why? Because in both 1 is mapped to 1. Over here 2 is mapped to 3. Over here 2 is mapped to 3. Over here 3 is mapped to 2. Over here 3 is mapped to 2. So they are the exact same permutations. And so the answer is no. Yeah, so only C generates S3. Let's look at the next one. So let C be a mod 3 mod 2 circuit of size S. Computing an n-bit function f, pick the smallest upper bound on the size of a permutation branching program over S3 computing f. Order S square, order n s square, order S, order n s cube. So which of these is correct? It's order n s square. Yeah. This we saw in class. The next problem is that, oh, I need space for this. Okay, I'll just look at next page. Yes, so let P be a permutation branching program over S3, computing a function f. Let S be the size of P. Pick the least upper bound on the size of a mod 3, mod 2 circuit, computing f, according to the simulation that we saw in the lectures. So let's recall what the simulation was doing. So let P be the program. First, we replaced and to do uh, this blew up the size by 2, right? Because we had to take every such instruction and replace it by 2 such instructions. So size is 2s. Then we used uh, HG. And this makes this size. So every G might become G square, right? So this means size is 4s. Then all the instructions containing H give E or G. And depending on this, check if all instructions containing H E slash G in the first case or G slash G square in the second case when H is G. So for all of these 4S instructions, you just need a mod 2 gate. So 4S mod 2 gates and one mod 3 gate for checking this. Yes, you need 4S plus 1 gates. The answer is 4S plus 1. Yeah. So let's look at the next problem. The next problem is called the probabilistic construction of the parity and AND circuits computing OR with inverse polynomial error used in proving the theorem of Allender and Hertram. What are the parameters of the circuit with the smallest upper bounds for each according to the construction? So the top Fanon order n to the order n log n into the order log n into the order log square n into the order log square n. So top Fanon is n to the order log square n. So it's either this or this. The bottom Fanon is order n to the log 4n or n to the log cube n. Well, this is the order n to the log cube n 4n. Why not take it again? Yeah. So the bottom one is order n to the log 4n. So C, and also random bits are in order log cube n. So yeah, C is the correct answer. So let's look at 6. So it's a probabilistic circuit for or if instead of probability 1 over poly n, we wanted an array probability of n to the minus omega log n, how many random bits are required if we follow the construction in the proof? Order log 4n, order log square n, order log cube n, order 2 to the root log n. So recall that we call it C prime with error uh, with constant error uh, and uh, order log square n random bits. The n to the omega lost my train again. Okay, yeah. So n to the omega log n is 2 to the minus omega log square n, and we have one circuit C prime with constant error. Now we need 2 to the minus omega log square n error. So we need omega log square copies of C. So we need order log square copies of C. Yeah, this will suffice. So order log, it's, yeah, this one. So let's look at the second question. So let C be a sigma A, pi B, sigma C, pi D circuit where A, B, C, D are respective families. If C is to be converted into a sigma pi circuit, what are the families of the corresponding sigma pi circuit? Top one in C, A to the B, bottom one in BD. Top one in A, C to the B, bottom one in CD, and top one in A, B to the C, bottom one in C. Okay, so let's look at bottom one first. Okay, so as a degree. So think of this as a circuit coming a polynomial. So its inputs are variables, this comes a polynomial naturally. And the degree of this is BD, right? Why? Because here and here are the only places where you are multiplying. So over here the degree would become D. Over here you would have a product of polynomials of degree D. Ah, let's mention that. Yeah, so and there would be many such products, so the degree can be at most BD. And degree of beta. So beta equals beta. Yeah, because in the worst case, this can be exactly BD and this can be exactly beta. Yeah, so BT. Yeah, so it's either this or this. So now let's look at the top one. So a pi b sigma c uh, m11. So it's a product of uh, d many polynomials. Each and every polynomial has c monomials, and each and every monomial has degree d, right? For that, I1 to IB, M1, I1, M2, I2, all the way up to MB, IB, right? So it has top channel. Okay, so if I represent this as, then alpha is, so how many alpha is equal to the number of tuples of the form I1 to IB? How many such tuples are there? Yes, for I1, you have C options. I2, you have C options. And IB, you have C options. So it's C to the B. Then alpha prime is equal to A times alpha. So it's A times C to the B. Because I need alpha many summons for each of the pi, sigma pi subcircuits, right? So it's A C to the B. Yeah, so it's A. So now let's look at the last problem. So last problem is let m greater than equals to 1, S be a subset of 0, comma 1 to the m, be non-empty, let W1 to Wn be chosen uniformly at random and independently. S0 is S, Si is P in S that P out the probability that there exists an I so that Si size is 1. So options are 1 over 16, 3 over 4, 2 over 3, 1 over 4. So this is the Savali-Mazrani theorem, right? And we saw in class that this is 1 over 4. So that's all I have for today. So there will be one more extra session on Thursday, this Thursday, from 6. You will get a notification for that. And in that class, session, we'll cover week 12 assignment because week 12 assignment's deadline is the day after tomorrow. Right? Yeah. So that's it for today. See you. Bye.